Hi, everyone. We were we're looking at calculating snow depths using ICESat-2. As you can see, we're a pretty large group, so working on a lot of different stuff. Yeah, I guess I'll just jump right in. No, let me go to the next slide. There we go. Okay, so our overarching goal for this project would be to estimate snow depths at mid-latitude regions by comparing ICESat-2 data to snow-free DEMs. This is definitely not something we were going to accomplish in this week, but continuing this work forward, this would be kind of what we're working towards. For this week, our goals included learning some of the new tools to work with ICESat data, developing Python skills, exploring and comparing methodologies. A lot of people in our group were new to either working in Python or working with ICESat-2 data. So there was a lot of learning and exploring that was happening. Nope, there we go. Going over a little bit of background on why we were interested in this project. Snow is an incredibly important water resource for many parts of the world. In the continental US, I believe about 70% of the continental US relies on seasonal snow for water. So understanding how much water is in a snowpack is really important, but is also really difficult because snow is extremely spatially variable. A depth measurement at one place might be completely different a few meters away. So that makes measuring that hard. Also, a lot of snowfall is in really remote or difficult to traverse terrain. So gathering field measurements where you're going out and collecting depths by probing is hard. You can't do that on a huge spatial scale. So remote sensing techniques become really important. LiDAR has really expanded ability to study snow depth. Current methods that are used are terrestrial LiDAR and aerial LiDAR from a helicopter or a plane. And this figure here from Deems et al. Shows the basic methodology of how we would be calculating snow depth using a LiDAR data set. Where we have a snow-free DEM and a snow-on DEM, and we compare the difference. And we're hoping that ICESat-2 can be a new source of this snow depth data. While the terrestrial and aerial methods really expand the amount of terrain we're able to look at, it's still restricted in how far we can look. And ICESat-2 is all over, which is awesome. Yeah, some of the challenges that come with comparing ICESat-2 to reference DEMs is the fact that it's pretty hard to co-register these. ICESat-2 is at an angle that's not going to be nicely lined up. Data resolution can be difficult, especially in really rough mountainous terrain. So getting that difference between the two DEMs, even in snow-free tracks, is hard. That's probably one of the biggest challenges we ran into. Yeah, and then this little drawing here is giving an idea of kind of what a ICESat-2 ATL08 footprint compared to a DEM might look like. Yeah, and I will pass it on. All right.
Do you want me to touch on this slide?
Sure, why don't you take it away?
Cool, okay, so going off of that, we wanted to really narrow down our scope. So we just picked one ICESat-2 product. Initially, we were thinking of applying this to a bunch of different locations and comparing ATL08 to ATL06. But once we got started, we realized, let's just pick one product, look at maybe two sites. So we looked at Grand Mesa in Colorado and Moores Creek Summit in Idaho, because we knew that there were validation observations or ground observations of snow. And then we chose somewhat ambitiously, I would say, a few different DEMs, one of them being SRTM, and the other is Copernicus, and folks also worked on the Airborne Snow Observatory data set, but we didn't have a chance to compare those to ICESat-2. Next slide. So just briefly, one thing we worked on was pretty early on was pulling those snow depths from SNOWTEL stations in those study sites. And sorry, this locator map is not incredibly helpful if you're not familiar with the area, but the orange dot, that tiny dot up in the upper corner, is Morris Creek Summit over in Idaho. And then we have our 2 Colorado stations, or Grand Mesa. So this is giving us a sense of the magnitude of snow depth that we get in one season. So we decided just to look at 1 year, from 2020 September to 2021 May. And you can see we get maximum snow depths ranging from about 45 to 85 centimeters. So that also gives you a sense for how accurate we want our estimates to be. We want our method of comparing the DEM to ICESat-2 to be within a few centimeters. So definitely less than a meter, because that's more than the full snowpack in these areas. Next slide. So the first DEM I mentioned, SRTM, we actually had folks working on different ways of pulling this DEM, because there's a few different methods. And the one we ended up going with most successfully was through Google Earth Engine, I think, which the tutorial yesterday really helped with. And so once we got that working, we were able to extract the SRTM elevations along one ICESat-2 track. So this is an attempt to compare the elevations in snow off conditions, because basically during this time period, we would want the difference to be 0 in snow off conditions when we compare those elevations. But you can see they're not. And I think Désirée will show us some helpful figures with that later, why that is. But yeah, I think this is demonstrating to me how just the vertical offset is not enough. We have to consider the 3-dimensional possible offset between ICESat-2 and the DEMs we're working with. So this is one example of that. Next slide. I just wanted to briefly show, we tried doing this for all the other ICESat-2 tracks in that time period, just over the winter. And this needs to be debugged at the moment, but we were pretty stoked to even get this working with pulling SRTM and looping through all of those ICESat-2 tracks successfully, just getting familiar with how to pull all that data. But as you can see, something is off here, we suspect at this point, because it's saying the elevation difference at some points is up to 750 meters. So yeah, we just got this morning and didn't have a chance to go back through and correct that. Hopefully something small. Next slide, I think I pass it to Désirée.
Yeah, I think, yeah, now we're on the correct slide. One more, please. Can you hear me? Yeah, good. So we also tried the Copernicus DM, and on this slide here, you can see on the top the profile of the one track with the elevation. In blue, you have the ICESat-2 data, and then there's the Copernicus DM. We also adjusted the vertical reference, because also in one of the tutorials you heard that if you're working with elevation data, it's actually quite important to know whether you are looking at the ellipsoid-based elevations or geoid-based elevations. But even after making this in theory correct, our snow depths are still minus 10 meters in average. So here, if you on the lower plot compare look at the blue line, that's basically our snow depth. And that corresponds to the track in the map that you can see there. And everywhere where it's red, it's about minus 10 meters. So very obviously, we have to do some co-registration. Next slide, please. So what we have in terms of shifts here likely is both some vertical shifts. So that means the DM and the ICESat-2 tracks, or all of the DMs and the ICESat-2 track, they are somehow vertically shifted. And in addition, probably you also have some horizontal shifts, which also translate into vertical shifts, because if you are on a slope, then there will be some elevation difference resulting from some horizontal shift. And I think we have basically both of these present in both our DM attempts here, and probably with actually all DMs that we could possibly try. So definitely we will need some co-registration to get that down to some error that is comparable to the snow depth that we can expect, like 0.5 meter or so. Yes, next slide, please. And I'm handing back to Karina.
Okay, thank you. Yeah, so our next steps, as we've talked about, co-registration is our next really big hurdle that I'm definitely hoping to dig into after this. This is going to be something I want to work with going forward. Once we get that co-registration working, wanting to look at more sites, more DEMs, more tracks, just expanding analysis and doing more comparison of what is the best methodology to be using. We're probably going to need to average snow depths over a larger area to get a usable estimation for that area. Since individual or even pretty small scale estimates are probably just not going to be useful given uncertainties. And then also hoping to dig into using slide rule more, not something that had time to really look at during this week, but really excited to work with moving forward. And I think that's our last slide. Thank you very much, and thanks for a great week.